I'll sit and stand sometime. Is it all right, this one? Yeah? That's fine? Yeah. So we should start. Yeah, we'll just wait for another 2 minutes, just don't record it because first we give 5 minutes. So, yeah. Oh, the photograph, there is a problem, eh? That's good. So can you tell me until now, because yesterday what I was discussing about system identification, yeah, we can start or something like that. We can start. So, any doubts on that identification? Please be free. Yeah. Okay. Anything else? Yeah, that's a good question. Yeah, that's, yes. Any other questions? I will answer everything. I want to remember that. Your all questions are valid questions, yes. See here, normally, suppose I assume a model theta 1 P1t plus theta 2 P2t plus theta n Pnt plus epsilon t. Now, what happens, you see, if the system is linear, because you know this P1, P2, they are yk minus 1, yk minus 2, uk minus 1, uk minus 2. That is understood. Linear systems. So, while doing the linear system identification, let me first answer his question first. Linear system identification, you sit in the computer, you start giving the ANA, you start with ANA, first you fit a linear model with first order model. First you give NA is equal to 1, NB is equal to 1. First you start here. I'll tell you the problem later on. It is not correct. Suppose you are not getting good response. Now when you give NA is equal to 1 and NB is equal to 1, your model, so your model is yk is equal to theta 1 yk minus 1 plus theta 2 uk minus 1. Is it coming? Yeah. Yeah? Yeah. Is it coming? You're moving fast. No, it's not moving. Yeah, lecture 6. Lectures 6 and 6. Yeah.
Open with
PDF Express.
Stop.
Yes, stop.
Something here.
Just back how.
Yeah.
Open it again.
Yeah, I'm opening it again. PDF Express.
This thing.
Now full screen. Okay. Now just you start.
Now.
How to? So how to this remove this? And this one.
It's coming.
Now wait. Look.
It's coming now?
No, but still it is.
No, every time now, then it will disturb. But
No, I lock it. Better. How? Open it again.
okay. Now this one.
Yes, stop.
It's coming?
Okay. Now this one.
Now wait. be some.
No?
Teacher is not there.
If you,
We will just zoom.
yeah. Because every time I do it,
That's sometimes we don't know. But first day it was working
first
perfectly.
day is working perfectly.
Lecture 6,
Yeah, first day it is working perfectly.
Okay, like that. Very that. Very na? Okay, like that you do.
Yeah, yeah, yeah.
No need to start.
Now the question is, you start with NA is equal to 1 and NB is equal to 1. See the interesting thing which will come up now. And you estimate. So how many parameters we are estimating? 2. Okay. Then you find that things are not okay. The predictive outcome. Then what you do? You do NA is equal to increase it. NA is equal to 2 and NB is equal to 2. If you do it, then your model will be yk will be theta 1 yk minus 1, theta 2 yk minus 2, theta 3. How many parameters? Will total number of parameters. You see here, total number of parameters is equal to 2. Now, if you make this one, the total number of parameters becomes 4. And you find things are not okay. You go on increasing, right? Go on increasing. Now let's do it. Now things are not, interesting things will come. Now suppose you make it NA is equal to 5, NB is equal to 5. So how many parameters total? 10 parameters. Then you can go on doing it. And you find that at what point it is doing perfect, then that is okay. In linear system identification, normally what we do, we gradually increase by trial and error. Okay. And we see which terms, which one model will be fit, perfect, right? It is because by increasing the NA, NB from 1 to 2 or 1 to 10, the total number of possible parameters increases from 2 to 20, right? But the real problem comes, suppose the system is nonlinear. Suppose the system is nonlinear. Now you will find, I have got the slides, I don't know here, I think let me go to that slide, 1 minute, then you can know it, 1 minute. 1 minute. Yesterday I was teaching that you just do trial and error. You sit in the computer, you first fit a first order model, not good, second order model, third order model, fourth order model, and at least fifth order, sixth order is fine, right? Now the real problem comes with the system is nonlinear. Then nonlinear, then there are many things. First thing, what is the maximum lag, NA, NB? And what is the degree of nonlinearity? Second order quadratic nonlinear, cubic nonlinear, right? In a linear system, by changing it in the computer, the total number of possible parameters changes from 2 to 20. Now we saw it, right? But in nonlinear system, if you are doing the same thing, sitting in the computer, you see the number of possible parameters, 16, 31, 136, you see, 5,000. So you cannot do such type of trial and error sitting in the computer if it is non-linear. Linear systems, we do it like that, right? So in system identification, there are two things. What are two things? One minute. Let's see. What are the two things? Is it coming? Why it's not coming? What is happening? No, this one. This is because I just want to open a PDF Express. Yes, PDF Express should come. It's coming. Yeah, right. Now see here. What here? Yes. YT is equal to theta 1 P1, theta 2 P2, theta 3 P3, theta n Pn plus epsilon. This is the model structure, right? Two things important. One is you are fitting a model. You are getting the measurements YT, right? Also regressors. Now the question is, which term to be included into the model? Because I show you in the nonlinear system, under your assumption, the total number of terms is going to thousands. Then which term to include in the model? Because once you know which term to include in the model, then estimating the corresponding parameter becomes easier, right? So system identification has two issues. One is the structure selection problem. What is that problem? So I will give an example now shortly. Structure selection problem. That means out of all possible things, which terms has to be included? And then is parameter estimation. Then parameter estimation. And out of which structure selection problem is the most difficult problem, especially in the nonlinear system identification, because which term to be included? Because once you know which term to be included, other things become easier. I'm just giving an example. Suppose I give you a signal. Suppose I give you a signal f of t. Suppose I give you a signal f of t is equal to 10 sine omega t plus 2 sine 11 omega t. Suppose. And I ask you, just giving a priori information that this is a Fourier series. This is a Fourier series. This is for the a priori information. Okay? Now you fit a model, Fourier model. I don't tell you which frequency component is present. I say that I gave you this data, you fit a model, and the model will be approached as Fourier series. So what you will do? You will use a model of this form. You will use a model of this form, theta 1 sine omega t plus theta 2 sine 2 omega t plus theta 3 sine 3 omega t, right? Because I have told you that it is a Fourier series, right? And out of which, if you fit the model, you will find theta 2, theta 3, theta 4, theta 5, they all will be almost 0. Because that signal doesn't contain that, right? So you will find only theta 1 and theta 11. So we can, which the mechanism we should use to do these things? Which terms are present? That is the extremely important part in system identification. Say for example, mass spring damper system. Mass spring damper system, everybody knows it. That the dynamics, what is the dynamic? Dynamics. mx double dot plus fx dot plus kx is equal to u, right? Because someone has found it out, so therefore you are saying that. But how do you know it? Whether it is x double dot or x double dot q? Initially, suppose you are nowhere there, right? You have been given a data, you see, this is the data, this is the mass, and I am applying a force, I am measuring the displacement. Input and displacement data is given. Now you fit a model. What you will get? You don't know anything. So that means whether x double dot will be there, x dot will be there, or x will be there. These are terms. How do you know it? So which one is important? Term selection is the extremely important problem. That is called the structure selection problem. Okay. And second thing is, and I am not answering that thing here because we work in system identification in the structure selection problem because we know the parameter estimation problem is straightforward. Once you know the structure, it's simple algebra. Okay. Then another thing is, because yesterday I did not tell you, think in this way. I have got a vector like this. I have got a vector like this. This is the vector, let us assume this is the vector yt. Now you approximate it. You approximate it, right? This is what we are doing in identification. See, the first approximation I am doing it. I am taking one vector here, another vector here, I am approximating, right? This one plus this one is equal to this one, right? Another one. The same yt is here. The same thing I am approximating. If you sum them together, it will be like that, yes or no? Because I can sum all these vectors and I will come to this point, yes or no? So same thing can be approximated by so many different ways. How many possibilities are there? Infinite possibilities. Now which one you will prefer? Naturally you will prefer less number of terms. Which terms? That is the point. Which terms? Our experience says 700 data points is sufficient to identify any system. That is from our experience. Around 15 to 20 terms are sufficient for a reasonable good nonlinear system. 20 terms is sufficient. Don't go beyond that. If they are beyond that, then there is some problem. Right? Then which terms? Which terms you should select? So that is the structure selection problem. Now coming to your question, system identifiability. Suppose now here you see a relationship. System is yt is equal to theta 1 yt minus 1 plus theta 2 ut minus 1. This is the actual system, right? Now what I did, I use a feedback where feedback is equal to k into y. Now I substitute here, then this equation will change. The equation will change, right? So, and you identify that equation. So you identify the entire system, but the system actually, there is a term y, there is a term u, but by that feedback, This y is getting replaced by k into u. So the identification is lost. System has got a y term, but because you are doing some manipulation here, so things are changing. I'm giving an example, it's not clear yet, I'll tell you one thing here. You are all electrical engineers, right? Electrical engineers. Anybody has taught induction motors? Induction motors? If I got idea, then I can discuss. See what happens. Okay. If not that, let me explain with this way. Signal flow graph. Signal flow graph, you do it. Now suppose this is x1 and this is A and this is x2 and something here. What is x2? What is x2? A into x1. This does not mean x1 is equal to x2 by A. Got a point? x2 is equal to A into x1, right? This does not mean that x1 is equal to x2 by A, because this is the signal flow algebra is different. Because here this does not permit signal to transmit in the other direction. Okay? So equations, you see here, I'm just giving an example here. Suppose the system is yt is equal to theta 1, I'm just doing it here. Yt minus 1 plus theta 2 ut, this is the actual system, right? I use a feedback ut is equal to k into yt. Suppose I use a feedback, ut is equal to k into yt. Now, if I substitute here yt is equal to theta 1 yt minus 1 plus theta 2 into k into yt minus 1, clear? Right? So that is equal to theta 1 plus k into theta 2 into yt minus 1. Do you understand these things? So this one and this one, they are algebraically equivalent, right? Because this is the same thing. Yt is this one, now ut is this one. Substitute that value and put it. But identifiability is lost. Because here, the system has got only y, u is not there. Whereas actually the system has got y, u. You got my point? This is called the system identifiability is lost. Yeah, there must be a term in terms of u, but it is no longer there. Okay. So, there are so many things has to be, the system identifiability is lost because of the closed loop system. System becomes closed loop, then identifiability is lost, right? But important point is the structure selection, not the parameter estimation. Because around 90% of the system identification literature is flooded with parameter estimation. That means the structure is known, but the real story is the structure selection. Because once you know the structure, the parameter estimation is straightforward algebra. So system identifiability is lost. Clear? Okay. So you are all academics, so you can say what we teach, the E is equal to minus n. When I was teaching electrical technology, while I was in REC, I was telling these things. Sometimes in machine theory, I taught 3 years I was teaching machine theory in Auckland. E is equal to minus n d phi by dt, electromagnetic induction. Now we say it, the negative sign is not the arithmetic negative. Negative sign is essentially reflects the Lenge's law, which tells that the effect always opposes the cause. Now this negative sign is not a arithmetic negative. I always say that. This is not an arithmetic negative. It maps, it models the phenomena of Lenge's law. See here. Lenge's law, what it says? E is equal to minus n d phi by dt. What it says? The voltage which will be generated and the corresponding current and the corresponding flux, it will oppose that, right? So it is the Lenge's law which is getting modeled or represented by a negative sign. Got a point? So those type of concept has to be there, right? Okay. Did you people did the assignment yesterday, the tutorial? Okay, you've done it. Okay. I'm coming to this point. This is which lecture? Lecture 6, 2, 3, this is lecture 6. Yeah. Today with these 3 lectures, you will know about adaptive control. The basic thing is, am I sitting, is all right? Okay, then I'll start sometime later. Yesterday what you did, you have got a system. You generated the data applying a pseudo-random binary sequence. You collected the entire data and use it in the identification. Clear? These things you have done it, right? PRBS sequence is given. Then there is the ID data object in identification toolbox. Just put it ARX, ARMAX or anything will do. That type of estimation is called the batch estimation. That is called batch estimation, where you use all the data together, right? That we will not do in control engineering. Batch estimation, we have to do as the data comes, one after another, one after another, you will go on estimating it. You will go in it. So that is called the online estimation, and it is coming under the category of recursive estimation. Recursive estimation, okay? Let us see the concept of recursion. You see, first let's go to the concept of recursive computation. That is only necessary now to understand. Now suppose I want to calculate the mean value of a sequence of samples. I have got 1000 samples data. I want to calculate the mean value. What is the mean value? I have got the samples. I have got samples Z1, Z2 up to Z1000. What is the mean value? Z bar is equal to sigma. Yes, sigma I is equal to 1 to n Zi divided by 1000. Sorry, divided by n. Right? I take the entire, all the samples, add them together, batch estimation, right? So how many storage space I require? 1000. 1000 storage, I have to store everything and then add them together. Clear? Batch estimation. Now let us do the same thing recursively. Recursively, right? So assume like that you are here, the data sample is coming, and you have to calculate the mean value, right? First sample comes. The first sample comes, what is the mean value? Mu1 cap. Mean value mu1 cap will be equal to Z1 because you have got only one sample. So the mean value is mu1 cap is Z1. Clear? The second sample comes. When the second sample comes, then mu2 cap should be equal to, first I am writing the general formula, Z1 plus Z2 by 2, that is equal to Z2 by 2 plus Z1 by 2. Clear? That is equal to Z2 by 2 plus half of what you have estimated before. Third one, the third sample comes. What is mu3 cap? Z1 plus Z2 plus Z3 by 3, right? So that is equal to Z1 plus Z2 by 3 plus Z3 by 3, right? Now that is equal to Z1 plus Z2 by 2 into 2 by 3 plus Z3 by 3. Is there any problem? I just manipulate it. That is equal to 2 by 3 Z1 plus Z2 by 2. That is equal to mu2 cap. That is equal to mu2 cap plus 1 by 3 into Z3. That is called mu3 cap. Right? So, as the samples comes, what I am doing, so in general you will see the general mu n cap. In general, the mu n cap will be n minus 1 by n into the previous estimate, mu cap n minus 1 plus the present sample 1 by n. This is the recursive computation. How many storage space I require? 2. 2 storage, right? Most of the batch processing algorithms, not all, I will tell you, not all, most of the batch processing algorithms can be made recursive. That point I am not explaining here. Most of the batch processing algorithms, where you take the entire data and do it, can be computed recursively by simple algebraic manipulation. Right? So similarly, now what we do it now in least square, batch least square, we will change it to recursive least square. Because that is what I need it. That is what I need for my adaptive control. Because each time instant, when data is coming, I will estimate the parameters and design the controller. We'll see. Okay? Now the same, I'm again repeating the point. All the batch processing algorithms can be made recursive or online estimation, real-time estimation or online estimation, the same thing. Here, suitable for online processing. Batch least square is computationally expensive for online estimation. In real-time systems, we require fast convergence, efficient memory use, update of estimates as new data arrives. Recursive least square or RLS fits these things. Suppose the system equation is yt is equal to phi transpose t theta plus epsilon. You see what I'm doing here? If yt, I'm just writing 3 terms, is equal to theta 1 yt minus 1 plus theta 2 yt minus 2 plus theta 3 ut minus 1 plus epsilon t, that is equal to yt minus 1 yt minus 2 ut minus 1. The parameter vector is theta 1, theta 2, theta 3 plus epsilon t. Clear? I am taking 3 terms without making complex. That is equal to, this one is called the observation vector. This terms is important. This is called the observation vector. This is called the observation vector. So this is called to, as I told you, any vector means it must be column vector. If it is row vector, then you transpose it. That is the standard practice. So that is called to phi transpose t into theta plus epsilon t. Where phi transpose, phi t is the observation vector. Any problem? Again repeating, any vector in engineering is a column vector. If in your expression you find any row vector, you transpose it. So now that means here, by definition, phi t is equal to yt minus 1, yt minus 2, ut minus 1. This is the column vector. Vector means column, right? Now suppose your system is yt is equal to phi transpose t into theta. And I want to minimize this particular modeling error. We will talk about lambda later on. Just don't worry, why I want to minimize this error, right? Now, the batch processing says, batch processing will say theta cap is equal to say capital phi transpose, all the data is there, into phi inverse into phi transpose y. As I told you, y is equal to x theta, x transpose x, whole inverse x transpose y. The same thing here, phi. Phi transpose phi inverse, phi batch processing. This is the theta cap batch. Theta cap batch is like that, right? There is a way to derive the equations, how to get the recursive formulation. That I am not going by, that itself will take more than 1 hour. That x, in this example, that x is phi. Here in this, x xt is equal to phi t. That's same thing. Because while making the class notes, this theta cap recursively can be computed. Theta cap t plus 1 is equal to theta cap t plus kt plus 1 into epsilon t plus 1. So these are the 4 equations which we will use to recursively compute theta, right? Now I will discuss on this. I am writing this equation in different way. Let us write down these equations, same equations. I am writing theta cap t is equal to theta cap t minus 1 plus kt into epsilon t. Do you understand this thing, first equation? Theta cap t plus 1 is equal to theta cap t plus kt plus 1 plus epsilon t plus 1, right? So I am writing in different way. Theta cap t, instead of t plus 1, I make it t. So once you make it t, then the t will become t minus 1. T minus 1 plus kt into epsilon t, right? The standard recursive computation in any signal processing or control or any subject, the present value is equal to the past value plus some gain and error. Standard formula. The present value is equal to the immediate past value. So immediate past value plus some gain into error. This is the standard structure of most of the recursive algorithms. The present value is equal to the immediate past value, theta cap t is equal to theta cap t minus 1, plus some gain into error. This can be derived. We can derive it. Mathematically, we can derive it. It is not a big issue. You know, it is not a very big issue. Derivations, I don't know whether I've given in here, but usually we ask the students to derive it. So now here, you want to estimate recursively, so present value of estimate is the previous value of estimate plus gain and epsilon t, the current error. Now here to estimate these things, you see here, you are estimating theta cap. So theta cap at a time instant t. Here you must be careful where you are. You are at time instant t. So if you are in t, what you know? If you are today, you know what we have discussed yesterday? So you know theta cap t minus 1. That is known. No doubt. So to compute this expression, this is known. This is known, right? Well, because you are at time t, so you have to know what is this. And you have to know what is this. Because to compute theta cap t, right? Theta cap t is equal to theta cap t minus 1, which is known, plus some gain and error, right? Present error. So you have to compute kt and epsilon t, right? Now see, what is kt? Now see here, this expression, equation 3. kt is equal to pt minus 1 plus xt or phi t divided by 1 plus x transpose t pt minus 1 into xt. Do you understand these things first? kt is equal to pt minus 1 into xt, right? 1 plus x transpose t pt minus 1 xt. Clear? What is xt? Xt, that is a phi t. That is the observation vector. So you are at time t, you are observing the signal. So xt you can formulate. Now you can formulate xt. We can formulate because xt. Clear? We can, because we are at time t. We are at time t, so we must formulate xt. That is there. That is xt is equal to yt minus tau, yt minus 2, yt minus 3, ut minus tau, depending on the model. So you know it. So you know you can formulate xt because you are at time t, you are getting the measurements, right? To compute kt, you require pt minus 1. P is the, I'm coming to that point, P is a covariance matrix. You see, this expression cannot be computed without knowing pt minus 1. See this expression. kt is equal to pt minus 1 xt divided by 1 plus x transpose t pt minus 1 xt. xt you can formulate. What is pt minus 1? What is pt minus 1? pt minus 1, you don't know it, right? Okay. Now the recursive computation, there is another catch words. I am just telling the catch points. You start doing something recursively, right? Any recursive computation requires one initialization, because where to start? Where to start? The present value is equal to the previous value plus some gain into error, right? Now what is the previous value? Previous value where? Previous value is 1,000 years before or 2,000 years before. Where the previous value? There is no previous point, right? So you have to assume some previous value to start with. So all recursive computation, all recursive algorithms requires some assumption that where to start. Got my point? Just like we said, whether chicken is first or egg is first. It's a difficult problem. You have to assume something, right? You understand these things? So that is an initialization phase. So you assume all recursive computation. You have to assume, because you see where I'm coming from. Let me just summarize before I proceed further. Theta cap t is equal to theta cap t minus 1 plus kt epsilon t. Theta cap, you are at time t, so theta cap t minus 1 is known. So to compute the entire expression, you must do kt and epsilon t. Epsilon t will come later on. Now kt is pt minus 1 into xt divided by that. You are at time t, xt is the observation vector, you can formulate it. Because you are getting the data, you formulate xt. So in this expression, xt is also can be known. But what about pt minus 1? Pt minus 1 is not known. So you have to assume. So not only that, in all the recursive algorithms, there must be some initialization phase. There must be some initialization phase, where you assume what is theta cap 0, p 0. When you start it, what is the initial value? You have to assume it. Otherwise, you can start anywhere, right? You assume that, then you start. Now, you are assuming these things. Now, this pt minus 1 is known, right? Because you are at time t. So, kt is known, everything is known, you got kt. Now, this pt, that's my initialization. Pt is equal to I minus k. See what is pt? What is pt? Let us write down. Pt is equal to I minus kt into x transpose t into pt minus 1. Right? So now kt is known. Xt is known because you have formulated that. Right? Now you can know pt. Right? Now once you know it, then this is straightforward. You get the current value, epsilon t, the error, epsilon t is equal to yt, because you are getting the value, minus x transpose t into theta cap t minus 1. Epsilon t. In recursive computation, when there are set of equations has to be solved, you have to first identify which one has to be computed first. There are 4 equations. Which one has to be computed first? Now you see here, in this case, this one cannot be computed first, because it requires kt plus 1, and kt plus 1 is the third equation, right? So first thing is, I'm just doing it here. First you do this one. First you compute this one. I will give you the annotated copy of this lecture note. Then after you do this one, then you do the second one, this. Okay? Then this third one, this is fourth. Right? Second and third you can interchange, is not a big issue. Second and third, yeah, you can do anything, but usually it's the case. The first you compute the Kalman gain, this kt is the Kalman gain, and then second, then third, then fourth. Okay, recursive computation. Initialization, you should initialize the parameters. What is the initial value of theta? And P is called the covariance matrix. I'm not entering into that. That is this matrix, this doesn't matter. So this P should be little high value. If you do not know the parameters, you should take it as a high value. Okay? Just initialize it. You will see now, the program. Exponential forgetting, I will come back. See, this is what equation I have written here. So this one, you should do it first. This one is the second. This one is the third. And this one is the fourth. Kalman gain. Pt into phi t. Lambda is the forgetting factor. I will talk to that one. Just assume that is 1. Phi transpose t, pt minus 1, phi t. I'll come back everything here. I'm just showing here. Now see, this program has been written. I'm just telling you this program is very carefully. Step number 1. Kalman gain numerator is equal to p into phi. Is it clear? Can you see the Kalman gain numerator is equal to p into phi. You see here. Numerator is equal to p into phi. Is it clear? Kalman gain denominator is equal to phi transpose into p into phi. Lambda plus. Now Kalman gain numerator, you see. See the program. Kalman gain denominator is equal to lambda, that's forgetting factor, I will come to that point, plus phi transpose p into phi. This is lambda plus phi transpose p into phi. Clear? Yeah? No, I'm using the forgetting factor, forgetting lambda, this one. That should be 1. No need, because I did not discuss now, I discuss shortly. It is lambda. What is that meaning of lambda? It is usual 1. Or what is lambda? I am coming to that point, just a minute. But the program is written like this, lambda. So Kalman gain numerator, Kalman gain denominator. So Kalman gain is equal to numerator divided by denominator. Clear? First equation is done. Then the covariance matrix update. P is equal to 1 by lambda, P minus Kalman gain into phi transpose into P. You see here? See, 1 by lambda, P minus Kalman gain phi transpose in P. See this equation? This equation is 1 by lambda, P is equal to 1 by lambda into P minus Kalman gain into phi transpose into P, right? Now see here, the same thing here in the program. See, P is equal to 1 by lambda into P minus Kalman gain KT into phi transpose into P. Clear? So K is computed and P is computed, right? And the error y cap is equal to this one. So error is equal to yk minus phi transpose theta, right? And then theta is equal to Kalman gain into error. Clear? Recursive square I am writing here. First equation, second equation, third equation, fourth equation. Any problem? Because why I am telling it? Because this is necessary for many cases, recursive computations. See the equations here and exactly the same way the program has been written, right? Okay? Now what happens? There is a term called forgetting factor. When new data, because you are estimating the parameters, as data comes, right? As data comes in, you are estimating, you are modifying the estimate. So normally what happens? You give either equal weight for all the data or you give more weight to the recent data. So that is the forgetting factor lambda. That is? No, that is not varying, that is constant. You see, 1980s when this recursive least square algorithm came up and all these things, people have done many research, the effect of forgetting factor. You just select this 0.9 instead of 1, make it 0.98, 0.99, this will work fine. It is not very critical in the performance of the algorithm. So therefore, the only thing that forgetting factor, you just forget by certain amount. Don't give equal weight to everything. Right. Yeah. Yeah. No, that will automatically taken care of whenever, if you derive it, that will automatically take care, because earlier we used to root it sigma epsilon square. Now I am doing it j is equal to sigma lambda k minus I epsilon I square. That's the only thing which I am doing here. If you do these things and do the differentiation, you will get that automatically, that expression will come. So instead of 1, if there is lambda, it means that you are giving more weightage to the recent data. Actually, you are not giving actually. That is, I'm saying this is not very important, because lambda is equal to 1. Instead of 1, you take 0.99. This should work. It's not a big issue. It's not very great. The performance of the recursive algorithms will not be affected much by these things. The only important point is any recursive algorithm is there must be some initialization phase. That's the point. And another point which I'm going to tell, and this is extremely important here, then before I go to the next lecture after some time, this point you will do it today itself, I am telling you. Suppose yt is equal to theta 1 dat, I'm just writing it here, theta 1 dat yt minus 1 plus theta 2 dat yt minus 1 plus theta 2 yt minus 2 plus theta 3 ut minus 1. See this very carefully. Yt is equal to theta 1 dat yt minus 1 plus theta 2 dat yt minus 1, right? Theta 2 yt minus 2, theta 3 ut minus 1, where suppose theta 1 dat is known. Theta 1 dat is known. It is known. Now, if a particular, you see, this is yt minus 1, this is yt minus 1, right? Now, I can make it as theta 1 dat plus theta 2 dat into yt minus 1, right? One term, right? But in the yt minus 1, theta 1 dat component is known. So, theta 2 dat is not known. So, if something is known, bring it to the left hand side. So, my equation will be, the estimation equation will be yt minus theta 1 dat yt minus 1 is equal to theta 2 dat yt minus 1 plus theta 2 yt minus 2 plus theta 3 ut minus 1. If something is known, don't estimate it. Bring it to the left hand side and other things you do it. We'll see to these things today in the next lecture when I talk about the minimum variance controller. Then I will connect these things, minimum variance controller here, and make it adaptive. Okay, we'll see. We'll have a break now. Your coordinator is very strict. Only 5 minutes break. Only 5 minutes break. These things say somewhere. Oh no. Yeah. Difficult to know.
Other side, this way.
This recording stuff, they have kept it, I don't know. Yeah. Yeah, yeah, you can put it. It's not an issue. Yes. Back side? Yeah. We are closer to adaptive control, self-tuning control now. That why I selected this minimum variance controller, because if you see, we'll see later on, there are a couple of many other reasons why I selected this one. This is the basis for developing future adaptive controllers, these things. Let me tell you a story behind this. This controller was developed in 1970s, 73 mainly, when the Automatica paper came up. The guy is Carl Astrom from Sweden. So he was assigned a task of the paper plant. In the paper industry, what they do, they want the thickness of the paper should be uniform. There should not be a non-uniform in the thickness. Okay? That means the variations around the thickness should be as minimum as possible, right? So they wanted that you design a controller which will minimize these variations. That is a Carl Astrom. So Carl Astrom, with one of his PhD students, they developed a controller called the minimum variance controller. Okay. Later on, it was found that this is the fast predictive controller. If you see it, this is the fast predictive controller. Okay, and there are many things I will tell you here, which is the basis for understanding the entire adaptive control theory. Right. Yesterday, I told you that while fitting any models, you must know exactly that why the hell you are fitting this model. Your fitting model is not a joke. It should not be considered as an intellectual exercise. If you are very clear that why you need a model, then you fit the model. I'm telling you, roughly speaking, I'll tell you, if you are given a set of data and you are almost expert, not fully expert, almost expert, not a layman. For unknown data, it will take at least 3 months time to fit a model. You see how much time it takes. You understand these things? It's not a joke, just put to, yesterday you put it ARX model and fit it. No, it never works like that. Okay, linear system is fine. Non-linear system is standard data sets. It will at least take 3 months time. With some, you have to be an expert, right? And people will just give you like that. Take a data set and fit a model, right? So I told you that you must know that what you want to do with the model, then you fit the model. Because you are designing model-based controllers. Minimum variance controller which you are going to study, it requires that the system must be represented by a Rmax model. You got my point? If the system is represented by a state space, minimum variance controller don't design. It requires that the system must be represented by this model. Clear? If the system is represented by different model, minimum variance control, don't apply it. Not that you cannot apply, but don't apply it. The minimum variance controller minimizes the variance of the output. Variance of the output means, say for example, the thickness of the paper has to be uniform. The variation should be as minimum as possible. Okay. We'll see many things here. See, this particular controller, it requires that system must be modeled by this one, right? It must be modeled as y of t yt is equal to z to the power minus k b by a ut plus c by a et. The system must be represented by this form. If the system model is different, then don't use the minimum variance controller. Now I am giving the concept here. This concept is extremely important, and that will carry forward for the generalized predictive controllers and many of our RP controllers which has been developed over the years. See the idea. Idea is very important. Carl Ostrom thought, why the variations occurs? There is a system, you are applying an input. The input is deterministic. Suppose the system has no problem, then why the output will have some variations? First question, it came to his mind. The industry tells me that you minimize the variations. The question is why the variations occurs? See, why variations occurs? Why variations in the output occur? First question. I have to minimize the variance, no doubt over that, right? Why variations occurs? Then Carl Ostrom found the variations are due to the noise present in the system. Then he found out, see the questions, it is due to the noise present. If there is no noise, there will be no variations. Clear? The objective is to minimize the variations. The first thing, if there is no variation, what is the question of minimization? So now he questions that why the variations occurs. He found that the variations occurs because of the noise, right? Now let us do one thing. See the mathematics where it's coming from. He told if the noise is the bloody idiot, it is he who creates problem, let us eliminate it. Suppose in this classroom, in this room, there are some idiots sitting there and they are creating problem. Remove them. Remove them, then everything will be fine. Yes or no? Very simple answer. Then you found it is not possible to remove all the idiots present in the classroom. It is not possible. Mathematically, we will show it now. Just a minute. It is not possible. Suppose in this classroom there are 3 idiots are there who are creating problems. If I could have removed all the 3, then I will get not a minimum variance controller, I will get a 0 variance controller. Because 3 people are creating problem, remove 3, what you will get? 0. Variation should be 0. But he found out, mathematically we will show now, that it is not possible to completely found out who are those 3 idiots. Complete noise estimation is not possible. If the complete noise estimation is possible, my job is gone, Professor Virakumar's job is gone, Professor Amal's job is gone, because noise is keeping us alive. It's not possible to do it, right? So then what he did, he told, okay, let's do it. We cannot completely estimate the noise. Let us estimate the noise, whatever is possible. And first we will estimate the noise from the given information. From the given information, we will estimate the noise. Whatever we will estimate, we will remove them. Understand the concept? If we can estimate everything, you will get zero variance, but not possible, right? So therefore, what he did, he took this model, he found this noise component is C by A. You see here, which is noise component? C by A, right? C by A. Now, he analyzed that what we can do, because this is the useless fellow. This component is the useless fellow. Let's see. Understand the concept now? Noise is the problem maker. Remove the noise. Ideal thing is completely estimate, remove it. But it's not possible. Let us do what we can do with the noise, and whatever we'll see. Minimum variance controller, let's see. YT, I'm again writing here, Z to the power minus K, B by A UT, plus C by A ET. Minimum variance controller essentially minimizes the predicted variance of the predicted output. Y square T plus K. It minimizes the variance of the prediction K-step predictor output. Right? So what is YT plus K? Let us see. What is YT plus K? YT is this one. So will be equal to B by A UT plus C by A E T plus K. Is there any problem understanding these few lines you have to understand, because I need it. Z triple minus K, here you see, Z triple this is Z triple minus K is there. So therefore, YT plus K means this gone, right? So we got only B by A UT, and C by A ET is here, so it becomes ET plus K, right? Now in this model, C is equal to 1 plus C1 Z to the power minus 1 plus C2. Why I'm telling these things? I'm coming to this point. C2 Z to the power minus 2 plus CNC Z to the power minus NC, and A is equal to 1 plus A1 Z to the power minus 1 plus A2 Z to the power minus 2 plus A and A Z to the power minus NA. Right? So, which is the component which is creating problem? C by A ET plus K, right? Now let us see what is C by A. What is C by A? Okay? C by A, this is the only thing you have to understand. Nothing else. Other things are straightforward. Now let us do one thing. Let us assume, suppose this is 1 plus A1 Z to the power minus 1 plus 1 plus C1 Z to the power minus 1. Simple. C by A, let us assume 1 plus A1 Z to the power minus 1 by 1 plus C1 Z to the power minus 1. So let us do one thing. Go to school now. Let us divide it. Now let's see. 1 plus A1 Z to the power minus 1 divided by 1 plus C1 Z to the power minus 1. I'm just doing few steps, right? So the first, sorry, what is that? 1 plus A1 Z to the power minus 1. First is 1. So this is 1 plus C1 z to the power minus 1. Subtract it. This will be A1, sorry, 1 plus C, okay. So 1 plus, yes? That's right. You are correct. You are correct. You are correct. 1 plus C1. Okay, let me go to the other side. Yeah, that's right. Thank you. 1 plus C1 z to the power minus 1 by 1 plus A1 z to the power minus 1. Only these things please remember now. Let's do it. This one I will take little time. I put 1 here, so I get 1 plus A1 z to the power minus 1. 1 minus 1 cancel. This is C1 minus A1 z to the power minus 1. Clear? Now let us assume, give it a name as alpha 1 z to the power minus 1. Just to, okay. So now I will put alpha 1 z to the power minus 1. So this becomes alpha 1. This becomes alpha 1 z to the power minus 1 plus alpha 1 A1 z to the power minus 2. Yes or no? Right? So if you again subtract, then you will get minus alpha 1 A1 z to the power minus 2. Right? Let us assume this is equal to alpha 2 z to the power minus 2. Right? Then you put it alpha 2 z to the power minus 2. If you do like this C by A polynomial will become an infinite series. That is the key. The key is this C by A polynomial will become an infinite series. That is C by A. If you do like this, I am not interested for this which value, I am not interested for that. That is called 1 plus alpha 1 z to the power minus 1 plus alpha 2 z to the power minus 2 plus up to something like this. You see, this C by A, if you do this particular division, it will be infinite series. It will be infinite series. Just telling one thing here, a simple division polynomial 1 plus C1 z to the power minus 1 by 1 plus A1 z to the power minus 1. How many parameters are there? 1 plus C1 z to the power minus 1 by 1 plus A1 z to the power minus 1. How many parameters? 2 parameters, right? That can be expanded into an infinite series. Do you know what is the meaning of that? A finite impulse response having almost infinite number of terms can be modeled by only 2 terms by a polynomial. One, see here, this entire thing can be approximated by only 2 terms, right? I think Steve Billings could found out this particular thing. Then he got a couple of students who was working on the rational model identification using this idea. Okay, I'm not coming to that. So C by A polynomial is an infinite degree, infinite series now. Then C by A ET plus K, because that is the idiot. Who is the idiot? Creating problem. C by A ET plus K. Now see this expression here. C by A ET plus K is equal to, if I multiply it here, I will get ET plus K, alpha 1 ET plus K minus 1, alpha 2 ET plus K minus 2, alpha k minus 1 et plus 1, alpha k et alpha k plus 1 et minus 1 and subsequently, right? Do you see anything here? See where I am coming from. Variations occur because of the presence of the noise. Let us analyze the noise term. By analyzing this noise term, he found this noise polynomial is an infinite series. He is at a time t, you are at time t, right? Now, if you are at time t, whatever is happening at time t and before, you know it, right? What will happen in future, you do not know it, right? Now tell me in this expression, which terms you know and which terms you do not know? Not known. Et plus 1, et plus 2, et plus 3, you see? Alpha k plus 2, et plus 2, alpha k plus. Whereas these terms you do not know, these terms are known. You see here? These are known. Or even EAT also this is known. Oh, dear. Why this is known because this depends on the past values, right? And this one, alpha k minus 1, et plus 1. Do you know et plus 1? You are at time t. Et plus 1 is not known. This is et plus 2. Previous one is et plus 2, right? Similarly, et plus k. You do not know. Right? So what do you know? You know the past values. Okay? So this is the idea. So what he did, he analyzed the noise term and split it into two parts. Which part he can predict, which part cannot be predicted. Right? That part which he will predict, remove it. So here, this particular part will always remain because it cannot be predicted, right? You cannot remove it. This will always remain. This will always remain. This will always remain. It cannot be predicted because this depends on the future values, right? So who will do it? This is the concept. Concept is clear or not? Concept is clear? Noise is creating nonsense. Predict the noise, and we found by analysis that the entire component, part of that we can know, part of that we cannot know, right? That part which you will know, remove it, right? Exactly the same thing. This is the mathematics. Another way of explaining is the C by A polynomial, I am not giving detail, is equal to F plus Z to the power minus K into G by A. So this one, this part is the first part which cannot be predicted. C by A is equal to F plus Z to the power minus K G by A. What I did it here this expression, this one, right? So you will find in adaptive control, in generalized predictive control, if you go, you are academics, you will go there, you will find this statement. Consider the Diophantine identity, C by A is equal to F plus Z to the power minus K G by A. This is the first statement. Adaptive control book, you go, generalized predictive controller, they will first tell, consider the Diophantine identity, C by A is equal to F plus Z to the power minus K G by A. When I started doing my masters, I thought, where the hell this identity is coming? Why it is coming? What is its significance? Actually, the significance is C by A is associated with the noise term. So let us, any polynomial C by A can be split into two parts. One is F plus Z triple minus K G by A. Okay? This F is the first term, few terms you see always remain. F is a remain. Okay? This one. And this is possible to show. This identity, I'm just coming here. Just a minute. This identity has been derived from the Aryabhata algorithm. Indian mathematician, 450 BC. Okay? These Britishers, it is all recorded, I am not bothered. Let the people listen. The people of Western people, they did not credit Aryabhata. They take it is Diophantine equation. Actually, it's not Diophantine identity. It has been developed by the Aryabhata identity, right? It's all there now. If you go to Google and you go to ChatGPT, you can also find out the Aryabhata algorithm, right? Aryabhata found out, Diophantine found out later on. Then another person, his name is Bejout. The same thing he found out independently, Bejout identity. What this identity is doing now, this identity is being used by Carl Ostrom. He took C by A, split it into two parts. One part and another part, right? It's possible. Show it. It's an identity, right? See, this part. C by A is equal to F plus Z to the power minus K G by A. Right? Now what he did, after splitting it, where the definition is F and G is there, right? Now you will find, if you put it, you will find, I am not doing the mathematics, y cap t plus k is equal to bf by c ut, that is mathematical you can find out, plus g by c yt, right? Yt plus k is equal to this one plus this one. You see the output has got two parts now. One is the predictable part, another is the unpredictable part, right? The predictable part consists of the actual dynamics plus small amount of noise part, because you cannot completely predict the noise, right? So this part and this yt, this is mathematically simple algebra. Now what he did, he want to minimize y. Now tell me, yt plus k is equal to bf by c ut plus g by c yt plus unpredictable part, right? I want to make yt plus k as minimum as possible. As minimum, ideally I should make it 0. But I cannot make it 0 because it has got two components. I have no control over f et plus k. I cannot do anything. So I can only do by selecting u, because u is under my control, the control input. I can only select, make this particular part what? 0. I can make this particular part 0, right? So which u will make it 0? If I make it u is equal to minus bf by minus g by bf, see, if I make u is equal to minus g by bf yt, then this particular part will become 0. Right? So what Carl Ostrom did, you see, I'm just giving the concept, I'm not going into detail into the theory. It is the noise which creates problem. So let us analyze the noise. He found that noise cannot be predicted completely. We can predict part of the noise, and other part we have to bear with that. We cannot do anything, right? So what he did, whatever part he predicts, okay, so this particular part, you see, so he made that particular part 0. He made that particular part 0. So therefore, and if you do these things, you cannot do it these things, the output y will, f e t plus k will always remain output. E is the noise, f is a polynomial, so that particular part will always remain. I will give one interesting thing to explain these things. When the minimum variance control came, if you are implementing minimum variance controller, first thing implementing a minimum variance controller, assuming 0 noise, is a complete foolishness. First thing. If you are assuming there is no noise and you are implementing a minimum variance controller, that means you are the third grade fool. You are completely useless. Okay, first thing. Then I have seen in some of the power system journal, during those times, when there is only one part, power apparatus and systems. Now it has been split. Some people, they will design a minimum variance controller and they will show that after certain short circuit, the delta angle became like this, you see, something like that. Time. Minimum variance controller performance. Minimum variance performance of the minimum variance controller for a sudden short circuit in a transmission line shows like this. Paper got published in Power Apparatus and Systems. The person who has reviewed it and person who has done that particular research, their knowledge on the control theory is not 0 but negative. Because the controller is the minimum variance controller. It is not a 0 variance controller. So minimum variance controller, there must be at least some variations in the output. You cannot avoid it. The true thing is, if it is a minimum variance controller, the output, at least in this case, you see here, there will be some sort of f e t plus k will always be there. You cannot eliminate it. What I point? You cannot eliminate it because the theory says the output variance will be f into e t plus k, right? You understand not understanding the control theory, then how he got it? The student may not have included any noise, so therefore he got it. If there is no noise, then what is the point of minimum variance? If there is no noise, why you are implementing a minimum variance controller? As academics, you must be very careful in this case. If the problem is faulty, problem formulation is faulty, there is no noise, you are implementing a minimum variance controller. U is equal minus G by Bf, because it is there. You got my point? So minimum variance controller means the output will have some variance. And the important point is, the noise component C by A polynomial can be split into 2 parts. One part you can predict, another part you cannot predict. What my point? Now, any questions until this point? See the concept here. If the concept is clear, that the minimum variance controller, so if you are doing it, so you will find later on, whenever you design any controller on the discrete parametric model, any book you go now, textbook, what they will do, they will say consider the Diophantine identity and they will use similar type of identity, right? What it does, it splits into 2 parts. Okay, this one here. Okay, and then the analysis follows. So some part they will predict, some part they will not predict. And as an Indian academics, I must tell you just replace that Diophantine identity, or you can combine together, you write down Aryabhata identity, okay? Diophantine, in my lecture handout, I give it Aryabhata identity, there is no problem, okay? So, this is the Aryabhata identity, or Diophantine identity, or Béjart identity. 3 people have done it, okay? This controller, you see, ut is equal to minus g by bf yt. Do you have any knowledge that this controller will be unstable if the b polynomial, if b polynomial has got any 0 outside the unit circle, because discrete system, this will become unstable. Yes or no? Because minus g by bf, b is in the denominator, right? So this is not suitable for non-minimum phase systems. Non-minimum phase systems not suitable. Not suitable. Because doctors are there to treat the patients. If doctor himself become a patient, then becomes a problem. What I point? So similarly, the controller is there to control the system. If the controller itself becomes unstable, then what will happen? If the B polynomial has got zeros outside the unit circle, it is in the denominator, right? Non-minimum phase systems, you know non-minimum phase systems, right? Non-minimum phase system means initially the output will go in the other direction. Okay, I'm giving a practical. My son always says, my dad is a clear example of non-minimum phase systems. Most of the father, they behave non-minimum phase towards their children. I'll tell you, I'm proving now. Anything your child will come and tell, initially you will say, no, you cannot do it. He will say, I want to go to the shopping mall. No, you cannot go. Then afterwards, you see, initially, no. Then afterwards, after some time, then some situation comes, your wife says, okay, he is telling and let's go. Then you will. You see, initial response is, see here. See, I'm plotting the response. Oh dear, why this is happening? Initially, the response will be negative. Whatever you say, initially no. Your boss, anywhere, everywhere the boss, they will do the same thing. You have to ask him, I want a conference leave. No, why you will go to a conference? Don't go there. Then after some time, you convince them, then they will say, right? There are several examples of non-minimum phase systems, right? A child, toddler is working, started working. Okay, non-minimum phase system. You ask him, you come forward, you walk. Immediately, instead of coming forward, he will go backward, 1 or 2 steps backward, then forward, right? So there are so many examples. So the minimum variance controller is not suitable for non-minimum phase systems, right? These things were developed by Carl Armstrong. See the concept. Then David Clark, who is the father of the generalized predictive controller, he was in Oxford. He has got a student called Peter Gothrop. 1975 proceedings IEEE, they found out another paper, Clark-Gothrop type controller. Just based on this criteria, David Clark and Peter Gothrop. Okay. They developed. They, as well as there is another guy in EMIST, I know all these people, they used to come to our university during that time, the Steve Billings friends. Peter Wollsted, P. Wollsted. He has written a book on self-tuning control, a very big book, will be published. They developed a generalized minimum variance controller, which I'm going to do, and you will do the assignment today. Generalized minimum variance controller, they generalize it. They generalize it. And what is that? I'm just giving the concept. instead of minimizing the variance of output, they try to minimize the variance of a function phi t plus k, not of yt plus k, which is a function of output, input, and the set point. Three things. This is the things which David Clark did it with Peter Gothrop. Okay? Instead of yt plus k, they did it. They formulated a generalized function which has got y, q, and r. It is same as the minimum variance controller if you take q is equal to 0 and r is equal to 0 and p is equal to 1. Okay, but they made it generalized. Now see the point of why, what I am trying to tell you here, the concept here. Who is the idiot here? Noise. Now this phi t plus k, simple algebra will say you, this is pb by qa ut. The noise component is not c by a, pc by a, right? Noise component is pc by a. This is the idiot who is creating problem, right? Who is creating these variations? Noise component. Now in this formulation, which is the noise component? pc by a. Now you see the formulation, straightforward, you can tell to your students, see here. Consider the identity pc by a is equal to e plus z to the minus kg by a. Analyze the noise component. Earlier what we are analyzing? C by a is equal to f plus z to the minus k g by a, right? Because C by A is the noise component. Now which is the noise component? PC by A. PC by A. So now we analyze that one, you split it. PC by A, some different name here. E plus Z to the power minus K, G by A. This G and that G is different, right? You split it. Right? So similarly, when David Clark developed the generalized predictive controller, his noise component is different. His noise component is different. But the same thing, he took that particular component, split it into two parts using the Arrhenius identity. Okay, and then other things are algebra, simple algebra. Just put it, substitute these things, that thing, you will get a solution. See the idea here. So when we were students, we were thinking, where this identity is coming, what it is doing. It's very difficult for the teacher who was teaching that to understand also. So we understood these things, that this essentially split the noise into two components, okay, and use it for this purpose. This generalized minimum variance controller is applicable for non-minimum phase systems. It can not only it can minimize the variance, it also can solve a tracking problem. It can track a reference. Minimum variance cannot track. Minimum variance controller actually is not a minimum variance controller. It is a minimum variance regulator. But this one is a tracking controller. By using the WT reference, it can track the reference. Right? Many types of control strategies, PI controller, PID controllers, can be designed by suitable selection of Q polynomial. So these are the ways. This generalized minimum variance controller has got so many advantages, right? Huh? No, this one will general GM will be applicable because you have got the freedom in selecting so many parameters P, Q, R. So adjust, you can do it. Now the control law will be ut is equal to minus gy minus hw by f, where it is defined f is equal to be plus qc and h is equal to minus rc, right? Hmm? Yeah. Which one? Now I'm coming to that point here. ut is equal to the number 5, please remember here, because I will discuss these things in the assignment today. This is the extremely important point here. ut is equal to minus gy minus hw by f. What is f? Is equal to be plus qc, right? f is equal to, just only this thing you try to understand now, then I will tell you. F is equal to be plus qc, right? Now tell me, what is q by definition? Q is equal to q0 plus q1 z to the power minus 1 until the something qnq z to the power minus nq, this q by definition. C polynomial is equal to 1 plus c1 z to the power minus 1 plus cnc z to the power minus nc, right? That is by definition, right? So forget about that higher terms. So qc, if I multiply qc, okay, there will be one term q0 plus something, you see, doesn't matter, I am not interested. The first term will have q0 because q0 is multiplied by 1, right? Clear? Without any power. Did you see it? Q is this one, Q is. Now let us go to BE. B because they are added. B is equal to B0 plus B1 z to the power minus 1, blah, blah, blah. C is equal to 1 plus C1 z to the power minus 1. Now if I multiply B into C, what is the first term? B0. B0. Now F polynomial, let's see now. F polynomial is equal to F0 in general structure is F0 plus F1 z to the power minus 1 like this. Now can you just tell me what is F0? F0 is equal to B0 plus Q0. Do you understand? F0 is equal to B0. This point is very important because this is necessary for our controller design now. F0 component consists of B0 plus Q0. Q0 is the component which you are controlling. That is the tuning parameter. You are tuning it. You know it. What you do not know, the system parameter B0. Are you convinced that F is equal to BE plus QC? F has got this structure. Therefore, F0 will have B0 plus Q0. Clear? This point please try to understand. This is the only point you have to understand. F0 is equal to B0 plus Q0. Clear? Out of which B0 is not known, Q0 is you are giving. So that is under your control. That is under your control. Right? Now you see here, I am not entering those things. See these things you will do it today. In adaptive controller, what you do, just like in the state feedback controller, U is equal to minus kx. If x is not known, you estimate x and put that estimate in the controller, right? Instead of U is equal to minus kx, you do it minus k into x cap, right? Now here in adaptive controller, what you do, you get the measurement online. You estimate the system parameters and put that estimation in the system. How it becomes adaptive? So as the data comes, Online you estimate it and use that estimated things here, right? So the step number 1 is you get the output. You know what is P, Q and R, that you know, that you give. Then you formulate this one. Phi t is equal to P y t plus Q u t minus K minus R w. W is the set point. Then you estimate F cap, G cap and H cap using this equation. This itself will take around half an hour to explain actually how to estimate these things. Anyhow, now F cap, F has got the structure F0 plus F1 z to the power minus 1 plus F2 z to the power minus 2. I am just doing 2 things. Okay, first term let us see. So phi t is equal to F0 u t minus k plus F1 u t minus k minus 1 plus F2 u t minus k minus 2. Any problem? The first term F cap u t minus k. Suppose F is equal to F0 plus F1 z to minus 1 plus F2 z to minus 2. So the first term will be, I am not using that, this phi t is equal to F cap F u t minus k. Is it F0 u t minus k plus F1 u t minus k minus 1 plus F2 u t minus k minus 2, right? That is equal to, here you see, what is F0? F0 component has 2 components, B0 plus Q0, right? So you write down, this is Q0 u t minus k plus B0 u t minus k plus F1 u t minus k minus 1, like this, right? Now out of which this one you know, your Q0 you are giving. So bring it to the other side. You will do it today, you will know it. So the estimation equation will be phi t minus Q0 u t minus k. This is in the right hand side is equal to the other things. You have to estimate these things. Okay. See here. While estimating the control parameters in step 2, use the estimation equation as this one. It requires, if you do not have a background, it requires little time actually to understand. So I have given the program, you will do it today. I am not telling that you can understand everything unless you do it before. Important thing you must carry forward is that a Diophantine equation which you are being used to do these things, essentially split it into 2 parts, noise component which is predictable and another is not predictable. That is the key point. Other things are simple algebra, you will see it. Once you do that thing, the other things are fine. So we will take a break. I think, see, here everything is here. What is the power and everything, all these things are given here. We teach 1 week course, 1 week for this generalized minimum controller in the, so difficult to, but I am telling you the important point here. And the program is, I think I have given the program in the, here itself I have given the program. At the end is there, yes. So at the end the program is there. See, F0 is equal to this one. This one. Yeah, minimum variance controller is very simple controller, so it can do it. Yeah. The only problem here is model predictive controller, which we are going to study now. Model predictive controller should not be used by the usual electrical engineers, because MPC has been designed especially for chemical process plants. Nowadays people are using MPC. MPC is computationally very expensive computations. And whenever a simple PID controller can do the job, why MPC? Model predictive controller is a hell. This one is also one sort of predictive controller, because you are doing YT plus K. You predict it. You are not minimizing the variance of the output. You are minimizing the variance of the predicted output, the theorem. Okay. This is also predictive control. Okay. David Clark developed GPC based on this thing, a different type of model, but similar type model. Similar control horizon, all these things. But I am telling you, MPC, our students are doing it because now we have to publish papers. We have to live with that. It's the situation like this. If you don't do it, we have to deal with that. But sometimes, as I told you, I don't like neural network, but I myself has published many papers in neural network. We can do it. We cannot help it. The student will say, I want to work in machine learning, artificial intelligence. I said, you should have a natural intelligence first before doing the artificial intelligence. Huh? Yeah, people don't think about that thing, right? Every time 100% students will ask, what are the poles of a system, control theorist? Poles of a system where the transfer function becomes infinity, I ask, where the hell you are getting transfer function? Where the hell the transfer, I am asking questions to you, what are the poles of a system? You are telling me where the transfer function becomes infinity, where the transfer function term came into picture. You got a point? So your understanding should be clear that the poles has nothing to do with this transfer function, because transfer function do not exist. First thing is the models, the differential equation model, transfer function, what you say, that do not exist. On the back of the mind, you should have that thing, that what you are doing is a mathematical abstraction. So that concept, our students now know. Our students now know. Now I told them that in future, if someone asks you what are the poles and zeros, so they are clear. At least that much they are clear now. So I want that you should also tell them the characteristic modes and what are zeros. You don't need concept of poles and zeros, and you will talk all these nonsense things. What's the point? Sliding mode based, MPC based controller. There is one student who has Journal of Energy Storage, who published the paper now. There is a student from China, Pengjing. Pengjing, we have published a paper and just sent a mail when I was in Goa. Dr. Swai, it was accepted in the energy storage. I told Jing, sliding mode controller with the MPC. No, I will do some multi-agent also attached. I don't know. For God's sake, don't do it. Don't do it. Multi-agent, sliding mode, MPC, observer. How many things you are combining in a power system problem? Everybody is doing it. We can't help it. We can't help it. Okay. Similarly, I'll tell you another important thing before I go to the MPC. We'll have a cup of tea now. Kalman filter, you see, Professor Veera Kumar knew it better than me. Kalman filter, you go to your academics, you find the students. Kalman filter, first you predict, then you take the measurement, then you correct that. Prediction, measurement, then correction. 3 steps. That is going to the brain of the students, it becomes difficult. You say, what is this? X cap, K cap plus, X cap minus. What is that? The 3 steps procedure. You predict, then you take the measurement, and then you correct it. 3 steps. So unless you know the fundamental things there, how people will do Kalman filter, extended Kalman filter, uncertain Kalman filter, particle filter, all those things. I have done it, I myself have done it. But I am saying Kalman filter is very powerful. How many people have studied, seen that paper, 1958, engineering journal, where the first paper of the Kalman came, 3-4 pages paper, 1958. ASME journal of engineering. Nobody. You got a point? So the things happen. We have to deal with that. We have to work. Although we know this is useless, we have to do it. Yeah. It will not eliminate non-minimum phase. Yeah, yes. I think non-minimum phase systems are little difficult to control, but I think most of the controllers, MPC and all these things can tackle the non-minimum phase. They can tackle. No, PID can control. Non-minimum phase, see, non-minimum phase. Yeah, I am giving the analogy here. The child is mischievous, but whenever he becomes young, then he will be, he becomes better. No, pole zero cancellation type controller should not be used under any circumstances. Under any circumstances, do not use any pole zero cancellation controller, because it has nothing to do with the system. Because you are poles and zeros, you are defining on based on a transfer function. The transfer function model has got poles and zeros, you see it. But that is imperfections must be there. So don't do it. Pole zero cancellations. Pole zero cancellation, we don't do it. And I will always advise, don't do that pole zero cancellations. Non-minimum phase system, little bit, it requires little bit more control effort, nothing else. Because initially he is not obeying you, but finally it will obey. I never seen any difficulty. Yeah. Tell me what the zero location is. Right hand side, yeah. No. Yes, that's a good question. No, there are controllers, pole zero placement controllers. It is there. It is the pole zero placement controllers. Sometimes I was teaching that, not pole placement, pole zero placement. Pole zero placement. We'll see. So we'll give you a break. Your coordinator, just to close the. Now you are given the free 5 minutes or 10 minutes? 10 minutes, yeah.
हॅलो चेक चेक आता येता मे बी आता पळय चेक कर ओके येता येता मदींच की बंद जाली बॅटरी हां तेका लागून
Hello? We'll keep it here or bit of thoda. That's fine. Yeah, that's fine. Still fine. Constituent people come. Yes. ठीक. Yeah. Difficult thing. Yeah. Hello? Hello? It's coming? Hello? 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 No? Hello? It's coming now? Yes. That's fine. Predictive control. Interesting thing. All the controllers, the classical controllers which you have discussed, they are reactive controllers. What is reactive controllers? Certain things happens and then they take action. The output is not equal to input, so then the measurement, then the error comes, then they take the action, reactive, right? Predictive controller are not reactive controllers. They predict certain things which is going to happen, so before it happens, they take the action. That is the beauty. Understand the concept of reactive controllers and the predictive controllers? What you do in control theory? You have got the reference, then you measure the output. If the output is less than the reference, then the error is there. It is going to the controller and the controller is giving the output. So that means the output has to deviate from the reference before the controller takes over, right? Predictive controller will not do like this. Predictive controller will based on a prediction. I will give one example of the predictive controller. Very typical example in my own house. We have got 4 brothers. When I was reading in one of the engineering college, oldest engineering college in Odisha. My brother was reading, studying in Odisha University of Agriculture and Technology in Bhubaneswar. I was in Burla. Then another brother was reading in Bhubaneswar in other college. Now see how it happens, how the predictive control works. In our village, we have got cow. During that time, cows are there, so they give the milk. Normally, we don't sell the milk, but the milk is being used for different purpose. Suppose there is a puja vacation. See the point, how the prediction comes in the picture. The puja vacation comes. So puja vacation suppose starts from tomorrow. So my mother will know that, okay, the vacation starts from this Friday. So my children will come either on the Friday evening or Saturday morning, right? So what she will do, knowing that we will come on Saturday morning, the milk which is there, which should have gone to other way, she will keep the milk. You see the predictive control. Predictive control, knowing that something is going to happen, not that we go there and we ask for milk, then she will keep it. No. That is the reactive controller. This is a predictive controller. They predict that this thing is going to happen, and accordingly you take the action. Okay. And most of the classical controllers, even the state feedback controller, they are all reactive controllers, right? The minimum variance controller which we studied now, which is minimizing the variance of the output, is essentially a k step ahead predictive controller. Because you are predicting what is yt plus k, okay? Then you found out what is the noise component, the predictor noise component, then this is the predictive controller, first predictive controller. Any predictive controller, how to predict? How to predict? In normal situation, we predict because of our intelligence. We know, we have got some information, so we predict that these things may happen, right? So for predictive controller, usually it is associated with the model predictive controller. We use a model, not for analysis, not for design of the controller, but for prediction purpose. This is name is model predictive controller, but actually it is used for predicting the output. Controller comes later on. The model is used for prediction. So in the model predictive controller, you take a model which will predict, right? Based on the prediction, you design the controller. Got my point? Nowadays you will find in the literature, people use the term model-free predictive controller. Model-free predictive controller. If you really look into that, I will tell you, there is nothing like model-free predictive controller. There is nothing like model-free predictive controller. When they say it is model-free predictive controller, so what essentially they do, they collect the data, do the online estimation that the estimator there, that the estimator is predicting the output. There is no explicit model. There is no explicit model for that, but they estimate it, right? So there is nothing like a model-free predictive controller. You have to do something how to predict it, right? So traditional controllers are reactive. Many systems require anticipation of future behavior. Predictive control uses a model to forecast the system output, right? Can handle constraints or input output naturally. Okay, let's see. This example, I got it from some book actually, but it's a standard thing. This example I've taken from book. This is not my example. Suppose you are going to cross the road, right? Crossing the road, actually this is, Indian people can understand it much better way than the foreign people. Once I was in Hyderabad in one conference. Two of my PhD students, they are from Palestine actually. Ihad Akila and his sister Lama, I think Lama is. So they came with me. I told her, I am going and you come, I will show you Hyderabad also. I have got some students working there. So I will tell her, I will organize the, car and other things, you don't worry for that. Those things taken care of. He told, okay, we will go. So what happens, the conference was in Osmania University. So we are staying in the town. The boss will come to take us to the conference site in the other side of the road. And we are on this side. Boss timing is there. So I will tell, okay, Yad, let's cross. Then Lama will tell, Dr. Swai, how we can cross? There are so many vehicles coming. I tell you come with me. You hold the hand of Yad, I am holding the hand of you hold the hand of Yad, I am holding Yad's hand. You come. Then we cross. Right? We know, I know because I am from India, so I know how to cross the road. Then Yad told, I'm a bit surprised. There are so many vehicles coming from all directions. There is no accident, and people are crossing. I don't, this is the beauty of India. Here, this is the real independence. Humans, dogs, pigs, anybody can cross. Everybody can use the road. No problem. It is not other countries, right? So this example, actually that is only valid for Indian scenario, that is not valid for foreign scenario, because foreign one you have to cross means you just see the light and you cross it. Otherwise, if you indicate that you want to cross, even if there is no crossing point, the vehicle will stop. That is the usual courtesy. Vehicle will stop and they will say, okay, you go. Very standard thing, very standard practice. Vehicle will usually stop. Okay. So, but let us say this is an Indian system. So when you cross the road, you see here, I will go to the other side. So first what I will do, I will take a step, I look. See the point, this is the prediction horizon. I will look whether some vehicle is coming or not. To both sides, I look it, right? I look to both sides. And I will estimate on my own mind, which the model will do here now. On my own mind, the speed at which the vehicle is coming, whether it will hit me or not. So based on that, I took a step. Not only that I took a step, if while taking the step, I suspect that some vehicle is coming very fast, it can hit me, I will retract. This is what we do it, right? We always look to this side, right? In foreign countries, doesn't like work like this. When you are driving, I will tell you, suppose there is a roundabout. I have seen many roundabout here. You don't see anywhere, you just see to the right. Vehicle is coming, you stop. Because that's the right of the way, almost all countries, right of the way. You just see the right side. You see all the people, when we are driving, we'll just look like this. No vehicle, cross. I am not looking whether vehicle is coming this side, that side. No. Right of the way. Okay. So it is different than India. So this is the typical Indian model predictive control is being extensively used by the Indians in their day-to-day life. So Indians can use the model predictive control. They use it in daily life. For them it is a play of a child. So just see what I am writing here. You don't just look at where you are, you predict. See, remember here, you predict based on your intelligence, right? Now what we will do here, we predict using what? A model. That's the only difference, nothing else. Okay. You assess not only current car positions, but also future positions. You start crossing only if the prediction shows no danger over the next few seconds. While crossing, you keep on looking, whether checking and revise your decision. This is the point. Key component is prediction, then optimization, then feedback. Depending on the situation, you do it. Advanced control strategy using system model to predict future behavior. Okay. Optimizes control inputs over the prediction horizon. I'll tell you later on this one, a little bit tricky thing here. Applies the fast control input. Okay. The core concept is you should have a system model. You should know prediction horizon until what time you will predict. Prediction horizon, cost function, and some constraints. Right. These are 3 steps. Predict future outputs using the system model. So model-free predictive control is a myth. It is not true. Actually, if you see it, they use one identification or estimation or something, a neural network or something, they will predict it. Solve an optimization problem to compute the optimal control inputs. They solve one optimal control problem. Apply only the fast control input. I will discuss these things. Repeat the process at the next sampling instant. Therefore, this MPC is very computationally expensive. MPC is very computationally expensive because each time step you predict, you solve the optimization problem, okay? You apply the controller and then predict next sampling instant. So therefore, when Manfred Morari did it, he did it for the process control systems, which is inherently slow. Because it takes time to do it. You are predicting, then you are solving an optimizer, right? It takes time, right? You can do it in microsecond. You can do it in milliseconds. It takes time, actually. So therefore, it is designed essentially for the process control plant. But nowadays, everybody is using the MPC, and the MATLAB. I don't know whether thanks to MATLAB or not. So MATLAB has got the MPC toolbox now. MATLAB has got all the toolboxes. Deep learning, reinforcement learning, all toolboxes. When I give the problem to the students, they will say, we have done the deep learning network. I told, deep learning network? Why? How could you do it? Professor Swai, we have got the toolbox. I looked to him. Yeah. Then I asked my student who is working with reinforcement learning. I told, Gunman, are you using a deep learning toolbox? Yes, Dr. Swai, I am using that. I thought I was thinking that you are writing your own code. No code. All are using toolbox. Everybody is using toolbox. Everybody is using toolbox. Hyperparameter selection. The term people use, you will surprise. Hyperparameter selection of the optimization algorithms. Why you tell parameter selection, why the hyperparameters? Where this hyper came? People, terms are used, that's fine. So you know why MPC shouldn't be used? Because very computational, very expensive, right? Receding horizon strategy, this is the point. David Clark used it initially in 1987 Automatica paper with one of the students. He used it. Manfred Morari, MPC came later on. First came GPC. I'm telling the history. Carl Ostrom, minimum variance controller. Peter Gotthard, David Clark, generalized minimum variance controller, followed by Peter Wallstead, we missed. Then David Clark, 1987 Automatica paper, 2 papers came. Generalized predictive controllers. 1990 Manfred Morari did it, Switzerland, MPC. And in between some variations came model algorithmic control, dynamic matrix control, in all the process control people. Because it is computationally expensive. Got my point? It is computationally very expensive. Even David Clark did not work with the GPC later on. Steve always says why David is doing all these things. He comes to our university doing the master's examination. I have seen him a couple of times. So 87 David Clark and 1990 Manfred Morari did this MPC controller which people are using now, right? Now one of the reasons, because you are academics, I am telling you, and when this Manfred Morari is doing this MPC, one group is working on that in Europe. There is another group, adaptive control, came up. Adaptive control, this is, you see, MPC connect with the estimator, it becomes all adaptive, nothing else. Any controller, just adaptive. Recursive least square estimator, it becomes adaptive, straightforward. Some people said these are all useless, they are mad people. Why to do the adaptive? Make it robust. Robust controller, parallel development, robust controller, asymmetry and robust controller. Okay, robust controller developed. 1990, robust controller developed. 2012, I was in Denmark in a robust control conference. Then there is a person, a keynote speaker was there. This keynote speaker is from USA, some Bala. His student is Carl Stoll, my colleague in the mechanical department. He was doing PhD with him. It's Carl's supervisor. He was there. All the people who came there, they said that robust control became very popular amongst the people. You know what is the reason? The reason is system identification toolbox, it came later on. Robust control found is 1990. I think within 1 or 2 years, MATLAB released the robust control toolbox. Mu synthesis, yes, unity controller, robust control toolbox is available to the people. MATLAB released. MATLAB did not release other toolboxes. And got a lot of money, right? So therefore, robust control becomes very popular. Robust control, we are not discussing robust control here, except the sliding mode control we will discuss. So you see, unless you know the history, you cannot appreciate how the things are happening. Okay, adaptive self-tuning controller, 1980s, 85, 90s. You will find hundreds and thousands of paper of self-tuning control, adaptive control, self-tuning control, adaptive control, which you are going to do today in assignment. Okay, take a system, put these things, RLS, recursive least square estimator, do it. Many power systems, O.P. Malik is in Calgary University. I think he has published, I think, not less than around 20, 30 papers, a power system guy. So many papers, adaptive control. So that stopped, right? So the people who work on adaptive control, that's fine. There is a guy in Automatica paper came, it's an interesting paper. Tomorrow I will discuss while talking about nonlinear systems. Linear systems, linear time invariant system, when controlled by a linear adaptive controller, understand this point, linear time invariant system controlled by a linear adaptive controller becomes a nonlinear time varying system. This is the proof in 1986 Automatica paper. What a point. I think Bitmead is the author, remember. So, you see what happens normally when you do research, we always want to see that, let us say what is the formula is there, write a program, get some results and publish it. But the real thing, where it is coming, exact point, it's very difficult. People will say, why you will study nonlinear systems? We are working on linear systems. No, it's not the case. Linear systems controlled by a linear adaptive controller becomes a nonlinear time varying system. 1986 Automatica paper proved. Did prove. One day, a seminar talk with Neil Monroe. He has done lots of work in Nyquist stability criteria and all these things. EMIST, he was there earlier EMIST, University of Manchester Institute of Technology. One day he was delivering seminar when I was there in Sheffield. Now you will surprise, I also don't remember that. The minimum variance controller, I told you, Carl Ostrom, David Clark, there's a Peter Wolstead who was in EMIST, was the colleague of Neil Monroe. Then Neil was explaining some theorem proposed by Peter Wolstead. Then he is telling, there are a couple of other people there. He told Peter did such a great job by deriving this theorem, and nobody remembers that, because people don't remember that. People will go to the algorithm and see it, because the theorem is important. Peter Wolstead, I remember, Neil Monroe told that Steve Banks, he was the editor of International Mathematical Control Theory. He was the head of the department at that time. He told, he's a Steve Banks. He told Steve, you also do not know. Peter did such a good job. You do not know. Only small theorem. See, we always forget those things, right? So similarly, you see where it come from, you must know these things. Otherwise, doing these things has no meaning, right? Let's go. Receding horizon control. This receding principle first used by the David Clark, later on by Manfred Murari. Continuously, receding horizon means you see it and you continuously look at, and as you go forward, you see further. Now you see until this point, if I go there, I will look a little bit further, then take my decision. I should go there, then I will look a little bit further. So that's the point. Unlike PID, MPC explicitly considers future system behavior. Control actions are chosen to optimize performance index. model-based decision making. Important point is, I'm telling you just an important point, the model which you are using, this is the important point. The model which you are using in the model predictive control not necessarily should be perfect. It is not system identification. Even if there is some model imperfections, still we can manage it. Still we can manage. That is the key point. Model may not be perfect, but you require at least a fast-hand model to do this. Just only simple mathematics. State feedback controller, linear quadratic regulator, linear quadratic Gaussian controllers, even robust controllers. All these controllers, in most of the cases, they cannot eliminate steady state error, which is a very important component. Got my point? Steady state error can be eliminated provided the system has its own integrating action, or you design an integrator. It is the integrator who has the capability to eliminate steady state error. Nobody else can do it. Optimal controller cannot reduce the steady state error to 0. No. You solve the matrix Riccati equations, okay? It cannot eliminate, right? An integrator must be there in the system to eliminate the steady state error, right? In most of the cases. Why most of the cases? I can take 100% cases, right? So what here, this formulation, what happens? One integrator is intentionally built into the model. System model is xm k plus 1, x dot is equal to ax plus bu. X dot is equal to ax plus bu. In our discrete domain is k plus 1 is equal to axk plus b uk, right? What they do? They integrate one integrator, okay? By integrating one integrator, what is done? They define a new state variable delta xm is equal to xmk minus xmk minus 1. The essentially integrator is, then they get this model. This is not actually model of the system. This is the model of the system with an integrator. Why integrator? Because eliminate the steady state error. MPC cannot eliminate the steady state error, right? So put an integrator at the beginning, right? That this model is being used now. Now our model is here. This is the model. This is the model. This is not the model of the system. This is the model of the system with an integrator. I am again repeating the point. This is the model of the system with an integrator, right? If you are not obliged to use integrator, if you are not using integrator, you can simply use that model. That is not a problem. It is not a problem, but at the end you have to use an integrator. Okay. So this is the model. Xk plus 1 is equal to axk plus b delta uk. But delta uk is equal to uk minus 1. This model is being used to predict the output over prediction horizon. Okay. What is yk plus 1? What is yk plus 2? What is yk plus 3? What is yk plus something, right? You predict based on this model. I am not deriving those things. Now if you predict it, you will find this prediction model will be like this. This y is equal to capital Y is the predicted value of the output, yk plus 1, yk plus 2, yk plus np, prediction horizon. up to what step you are predicting. This capital Y here, you see, this capital Y is the prediction equation, prediction, right? Yk plus 1, yk plus 2, yk plus 3. It is possible to do. So if you do it, this is the equation. This is the prediction, predicted model or prediction output. F is equal to Ca, Ca square, Cnp, and phi is this matrix. Very easy to algebraically you can find out. Once you get this prediction, then you minimize a cost function. Remember, this capital Y is a predicted output over a particular horizon. Again, repeating this point. Y is equal to, I am writing again here. Y is equal to Y k plus 1 given ki, Y k plus 2 given ki instant, Y k plus 3 given ki, similarly Y k plus np. Okay. So these are all predicted output. Okay. And what you do, this is np times, this is the reference signal. So that is a performance index. First you predict, then you optimize. Which one? This performance index. Reference minus the output into some weight and the control input, delta U, these things, just like here. J is equal to, I am writing a small way, R minus Y transpose R minus Y plus delta U transpose into delta U in general. Just a minute, I am just modifying these things here. In optimal control, we optimize J is equal to X transpose QX plus U transpose RU. LQR optimization. LQR optimization. Here, you are also doing optimization. What you do? Your performance index is R minus Y transpose into R minus Y plus delta U transpose delta U, right? And you are just putting another weight just to control. So that is the performance index is J is equal to, I am writing here, R minus Y transpose WY R minus Y plus delta U transpose W U delta U. This is the performance index. X transpose QX, U transpose RU, same thing. So first you predict by using a model, first you predict, then you optimize this performance index, right? Now it will give you, these are the weights, control weights. Now it will give you a control law, this is the control law. This is the control law. What I want to say, if you are using a model to predict the system, then you can use that particular performance index and get a clear-cut mathematical expression, just like phi transpose WY phi plus WU inverse phi transpose WY, these things, right? If a model-free predictive control, what they say, actual which is not, there the optimization is carried out in a different way. You cannot get a clear-cut expression like this. Because there is no model, you are estimating the model from the data, right? But essentially, you will not get this thing. That is the only difference. Suppose you are using a neural network to predict those Y, right? So therefore, you will not get any expression, a closed form expressions like this, right? Otherwise, there is no difference. So you get delta U. Then after getting delta U itself also has a control horizon. Delta U k plus 1, delta U k plus 2, delta U k plus 3. and you use the first one. Now the question is, are you a fool? If I am using only the first control input, then why should I compute the control input over a horizon? You understand the question first? He is telling that delta u is this. Note that the optimal control vector delta u contains here. Delta u ki plus 1, delta u ki plus 2, delta u ki plus nc minus 1, right? And you use only this one. The next step, right? Get the model, predict the output over a particular horizon, that is y k plus 1, k plus 2, k plus 3, right? Optimize that particular thing, you will get the control action. This control input has also its own horizon. And you use only the first control input in the next sampling instant, because it is online. This is online. Now the question is, we usually ask the questions to students. MPC will give you a sequence of control actions over k plus 1, k plus 2, k plus 3, and will ask you, use only the first one. That means it's just like this. You are going to have a lunch, so there are dishes. I will tell that in the dish, this is what, this is one dish, this is another dish, this is another dish, this is another dish, but you only take only first dish. No, then you will say, what the hell you are talking? You are giving me 10 dishes, and you are asking me that you only eat the first dish. Then why the hell you gave this 10 dish? You understand this point? It sounds ridiculous, yes or no? See the delta u k plus 1, delta u k plus 2, following the receding control principle, implement the first sample. Then if you want to implement the first sample, why to compute all these things? Now the question is something different. This can only be understood from the chess player. You see the chess player, what they do you know? When the person is playing chess, world champion, they know if I apply this control input, what are the possibilities that that fellow will do? If I apply this one, what are the possibility? If I apply this one, what is the possibility? If I apply this one, what is the possibility? You got my point? He has got 10 things in mind, but he will use only one. And then after that, depending on his action, then he will think. Got my point? The same thing is being, it's not myopic. We don't say, MPC is not myopic. MPC sees many things, but do only one. But he has got a knowledge. He has got a knowledge that these control actions, right there. Got my point? So you have got the model, you have got the optimizer, then you implement these things. Each sampling instant. Because you are doing it at each sampling instant, so therefore it is computationally very expensive. The system is very fast. It is always advisable that don't use MPC. Got a point? But if you want to publish papers, that's fine. I have nothing to say. We are doing it, you have to do it. Got a point? MPC should not be used in that place. Okay? Prediction horizon and the control horizon, NP-NC. 1987, when David Clark did it, NP-NC, because I was there in 1994. So, there are many people work. I'll discuss something. That what is the effect of the prediction horizon on the performance of the controller? What is the effect of the control horizon on the controller? To be very frank, I'll tell you, its effect is not that much significant if you have got a little bit of knowledge about the system physics which you are controlling. The NP should be 10, 20, you should find. Actually, theory is the settling time is there. You should, suppose your sampling time is 1 second and settling time is 20 seconds. So you take NP at least 20. Okay. Suppose you are sampling at 0.1 second, settling time is 5, so you take NP as 50. Just settling time, NP. And NC, less than NP, 5, 10 will do. So it is not very significant. We do not see any significance. That's my experience I'm telling. Okay? So nowadays nobody is doing, not only this NP and C, choice of sampling time. Choice of sampling time in system identification, in adaptive control, it is a major research area earlier days. Nowadays, sampling time you can select. So NP should be almost cover the settling time of the system. Okay. Settling time of the system. And 10, 20 should be fine. Only problem is it's computationally very expensive, very expensive. And I think today tutorial, I don't know, Professor Amal, did I give, MPC is there in the today's tutorial? So the MPC, I have got I have done it. Okay, one thing I'll do, because we're academics, I learned it during my time, I must share with you, which we'll do in the genetic algorithms also in this course. Practice active reading. What is active reading? I learned it from one of my friends from Singapore, Tiam Lin G. G will always come to my house and he will say, "Hey Swai, your wife can make roti paratha." I told, "What, G, you are telling roti paratha? Roti is something different, paratha is something different. What is roti paratha?" No, see, then when I went to Singapore, I found this roti, they said roti paratha. He will say, "You make roti paratha, I will take." Then G told me, active reading, I always do that. Suppose a recursive least square. There is no need of going much detail into the recursive least square. If you really need it later on, you just see the algorithm, write a simple code for a simple system and see how it is working and keep it as a file. Keep it as a file. Right? Active reading. Not that simple read, just read it. Say MPC, you know MPC how this model is there. Then you see, this is how the optimizer. Just do it, simple thing, and see how it is working. Then only, if you need it, then you use it. I'll tell you, genetic algorithms, I have done it quite long back. Because the genetic algorithm toolbox was developed by Peter Fleming by MATLAB to genetic algorithm toolbox which you are using now. It was developed by Peter Fleming. Peter Fleming was the head of the department, Sheffield University, automotive control department. Okay. So all big sorts were there in control department, all big sorts. Huge big sorts are there. Peter Fleming was a HOD in that time. He has got 13, 14 students working on genetic algorithm, out of which Carlos was working on this multi-objective optimization problem. So, genetic algorithm, I learned it there. I have got active reading, I put it. So one day, I think 2011 or something, we have got a student from South Africa, Michael NIT. We are working on the wireless power transfer. I was looking to the control aspect, a modeling and control aspect. By the time one model we have published in transaction power electronics. Then Michael one day come to me. I told Michael, just like it came to my mind. I told Michael, you do one thing. Why don't we use a genetic algorithm multi-objective optimization to optimize the parameters of the PID controllers for this wireless power transfer system? He told, I don't know genetic algorithm. Then I went to the computer, active reading. Genetic algorithm, simple code is there. Then I explained Michael. I told Michael, you come and I will explain you. That was around 3 o'clock. I told, okay, Michael. Michael told, I understood it. South African, white guy. After 2 weeks, I'm just going out of my office, just trying to go, right? Take the car and go. He knocked my door. I told Michael, what happened? No result. What result? What result? I'm asking like this, what result? Then that multi-objective genetic algorithm. And also, yeah, I told you last week, yes. Do you have time? Just see, I'll show to Uday later on. Uday is the main supervisor. But you just see, but you check it. You will surprise, I gave him a simple MATLAB code. Weeks before, he doesn't know about genetic algorithm. I explained him. He implemented in the software. Experimentally, he did it. He got the result. Make a draft of the paper. My paper is published in, we send it after 2 months, it got published in Transaction Power Electronics. Such type of people, I'm surprised actually. Just active reading. So I will always advise you people, do the active reading. Not just read it. Write a small program, keep it in your place. If some students come later on, you do it. I have been doing it for a long time. I've got another student working on this capacity power transfer, William Su from Taiwan. Then he wrote a flow chart of a controller. I told William, this is a fuzzy problem. What the hell you are doing here? You are writing a flow chart. He told, fuzzy logic, I don't know anything. I told, come to my office. I'll tell you fuzzy logic, I'll give you the code. Then I gave code to William. Then he did it, same thing. We published 2 papers. One is transaction in industrial electronics and the other is IET power electronics. It is because it is possible, because the active reading, fuzzy controller is there, membership functions define and how to generate fuzzification, defuzzifications, and you should understand that thing. Okay? Any questions here before we proceed? No. See here. Coming to that point. Yes, I'll explain you. You see here, XMK plus 1 is equal to AM XMK plus BM UAK. YK is equal to CM XMK, right? Now, suppose delta XM is equal to XMK minus XMK plus 1. Delta XMK. Then delta XMK plus 1 will be equal to XMK plus 1 minus XMK plus 2, like this, right? Delta XMK is equal to XMK minus XMK minus 1. XMK minus 1. Delta XMK by definition is XMK minus XMK minus 1. So delta XMK plus 1 will be XMK minus 1 minute. Just give me time. Let me do it. This will be XMK plus 1 minus XMK. Do you understand this thing? If I am defining delta XMK is equal to XMK minus XMK minus 1, then XMK plus 1 in place of K plus 1 will be XMK plus 1 minus XMK, right? Now this one If you do it, this will be EAM XMK plus PM UK, right? Because by definition, you see here XMK plus 1 is this one, right? Minus delta minus XMK. XMK is just you know, minus XMK is AM XMK minus 1 plus BM UK minus 1. Now you subtract it together, then you substitute, you see this is XM, AM, XMK minus XMK minus 1. That is definition in delta XMK, so this model will come automatically. So that way, by integrating, they get it. This thing has been, this approach is used by Liu Ping Wang. She's in Monash University, or sorry, in Melbourne. She's in Melbourne actually, this lady, this Chinese lady. Any questions, other questions? Tomorrow we'll study, yes. Linear quadratic regulator, good question. Linear quadratic regulator is a reactive controller. It is not a predictive controller because it doesn't predict. It doesn't predict anything, and certain things happens, and you take the actions. No. No, it's not a predictive controller. Okay, no, I'm explaining these things. I'm explaining these things. Your questions are very valid questions, no doubt about that. This is why. Now this is the controller. This is the system. So you get the system x1, x2, x3, right? Then you multiply by some gain k, you get multiply by gain k, and this one is going to here, and you apply it. It doesn't matter. Now here, system is there, it is producing the output, the state variable is there, x1t, x2t, x23, you measure it, then you are not predicting, you are not using x1 t plus 1 or x2 t plus 1 or t plus 2, you are not doing that. You measure it and you compare with the reference and then apply it. So yes. No prediction is used. LQR, no prediction is used. Yes. You are doing it, yes. It's not a predictive controller. You predict, and based on the prediction, you take the action. So therefore, it is a little bit powerful, similar to Kalman filter. We say why Kalman filter is very effective. You predict, okay? You predict that this fellow is going to do these things. Then you again take the measurements to check whether your prediction is correct or not. Then if you check it with your prediction, and if there is some error, you modify your prediction. So therefore it is powerful. And I will share with you, Kalman is the only person, Steve always tells, he's the only person who leads a life of a Hollywood film star. Because whenever he comes to deliver a lecture, people come during those times $2,000. And the audience is full. That fellow is from Hungary. His father migrated to USA. Ari Kalman. Very powerful Kalman filter. It is extensively used nowadays, Kalman filter. Any questions? No, 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 no. Based on the present time, you predict, right? Yeah. You are at time k, okay? You are at this time. Now you predict. See, I'm just telling, I'm just moving now. So I am here. Now I predict 10 steps. Here, 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 there, right? 10 seats I will predict who will sit. Then I make one step. Once I move one step, then I will start predicting 10. So receding, you see, I will still predict there. Now similarly, if I take this step, again I will predict.
But control horizon is 5, right?
Yeah, control horizon is 5.
But you are giving 5 inputs and you are predicting 10.
Yeah.
Instance you are predicting 10, right? So for 5 it should be 5, right? For last 5 outputs,
No, 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 it's not, it doesn't work like this. It doesn't work like this. Your optimizer is there. There is an inherent optimizer in the MPC, which is optimizing a performance index. Okay? So that particular performance index is taking how many steps you are predicting, okay, and giving a control input. That optimizer can give you. Optimizer has nothing to do with how many control horizon is there. It doesn't bother with that. Okay, I mean, so you predict, okay, and depending on, you see, how many control inputs you want, you tell to the optimizer will do that thing. Not that optimizer will tell, you are predicting 5 steps, why you are using 10-step prediction horizon. No, no, no. Optimizer will take 2 inputs separately. Got a point? 2 inputs separately it will take. It will not, your question is valid. You are saying that 5, then I will ask, why 5 input to control horizon, you are using only 1 input in the next step? No. You, just like the chess example I gave you, okay, although you use only 1 step control, but you think, if I would have used this control input, what would have happened? This control input, that's the point. It's a bit tricky things in the predictive control. And remember, for doing all these things, the prediction horizon and control horizon has no meaning. I mean, it is not that significant. You will find in many of the power system journals or any things, people get some results 97% accurate. Another will get 97.2%. Is it significant? You got a point? So NP and NC doesn't have significant, provided it is within the range. And your question previously that, because we are not discussing a constant one. Usually the input is constant, output is also constant. Right? So you have to constrain those things. If you are a layman and you do not have a constrained optimizer, you do one thing. You compute the control law just like this. Then you see, you compute the control law, then you say like this. Without any optimizer, if delta UK is greater than delta U maximum, delta UK is equal to delta U maximum. Just put it like that. That is a constant. But usually nowadays, quadratic programming, there are so many other solvers are there. There are so many other solvers are there. One time, how much time is there? Time is gone? Time is gone. Then we'll see. Because I will tell you later on, most of the cases we are solving these equations. But in stability studies, If it is a inequality, do you understand this? You can solve what is Ax is equal to B, X is equal to A inverse B. That is easy. But find out X when X is less than B. Just a difficult problem. Inequality. Inequality does not have a unique solution. Linear matrix inequality is an inequality. Equality is easier to solve. Inequality is equal to 1,000 solutions. Okay? So in that case, whenever the inequality comes, especially Lyapunov stability criteria and many cases inequality, then you have to find out of so many possible solutions, which is a feasible solution. LMI feasibility, they say it. Okay, you understand this problem very carefully actually. It's a equality, inequality, uniqueness, non-uniqueness. So those things are important. Solution is there, is available everywhere. We'll see.